All right, hello. Happy to be here. My name is Rumpf, and I'm a research assistant at the Department for Structural Design, headed by Manfred Grohmann at the University of Kassel. Today I have the pleasure to present some research to you that has been carried out in collaboration between the School of Art and Design and the School of Architecture in Kassel, together with Design to Production from Zurich. So Markus Chanin from the School of Art and Design and myself, we were supervising a 2-semester studio which was dealing with the question of developing and also fabricating a customized acoustic structure. And today I will present first of all how we were using various analog and digital methods in order to use sound as a design driver. And in the second part of our presentation, I'll elaborate a little bit more on the fabrication and installation of the realized ceiling. But in order not to keep you in suspense for too long, there is already an image of the outcome. But first things first, where did we start? The design location is the Office of Design to Production in Zurich. It's a box-shaped office with primarily hard, non-absorbing surfaces, and even the furniture has almost non-absorbing, sound-absorbing material. So the audibility was clearly perceivable as being poor, impeding, and hindering communication. I think you can ask Silvan, who presented yesterday, about that. This was also confirmed by a measurement of the reverberation time, which was approximately 1.3 seconds in average. So hence the aim was to improve the acoustic situation, but at the same time, we were asked to that the structure should represent the client's, like Design to Production's, working philosophy, which was rooted in parametric design. I'm sure you're all aware of Design to Production, and you know that they are specialized in parametric planning and digital fabrication of non-standard architectural objects. So in order to represent their working philosophy and their ambition, the ambition was to build a visually appealing and bespoke structure using simple means to skillfully answer complex tasks. In particular, the use of computational design methods were kind of not demanded, but were we thought about it. And consequently, the use of an associative modeling technique which relates simulation data to a geometry foundation formulation seemed to be a natural choice. If you weren't aware, you are by now, after that intense lecture by Chris, that simulation of various performance aspects is common practice in architectural design. However, the moment of utilizing these simulations varies from very early design stages, where it is used in order to explore design space and for geometry formulation, to very late design phases in order to prove an aspired performance of an already elaborated design. In particular, structural simulation is well established. You see the examples, like the physical examples of, again, Antonio Gaudí, this time not Sagrada Familia, but Colonial Güell, and also some work that was done at the University in Kassel, where structural simulation informed the form generation. In contrast, acoustic simulations is mostly used for predicting and respectively fine-tuning the acoustic performance of spaces where it is of paramount importance. Sound absorption, which is most of the time crucial for the reverberation time and thus important for the acoustic quality of a space, is mainly determined by material properties and not by macro geometry. Only if sound scattering plays an important role, geometry gains a significant role. We've heard that as well from in the presentation by Jane Burry in the morning. And also the Melbourne Recycle Hall is a descriptive example where the cladding is varied on 3 different scales depending on high, mid, and low frequencies. So there are various reasons why acoustic simulation is not wider spread in early design stages, i.e. in geometry formulation. There is still lack in reliable methods for simulating absorption and diffusion. There's obviously a performance limitation for modeling software and simulation techniques, which is particularly significant when you want to work with an iterative approach. But what we found most important, simulation techniques do not necessarily correspond well with the actual hearing experience. And I think this quote by Bill Edis puts it quite nicely when he said, "In the end, acoustic quality is judged by humans rather than measuring instruments," meaning that some subjectivity remains inevitable. All of this together motivated our decision to go for a more open, patchwork-like methodological setting. So, for example, we were having experiments with sound artists, in this case with the sound artist Wolfram Spürer, about the perception of sound intermediated via headphones by a potentially manipulated record. This is just a... well, it gives some kind of impression. So this helped us to understand sound as a spatial phenomenon expanding over time. Further on, we were working with custom-made Grasshopper tools for simple three-dimensional visualization of sound emittance. The initial tool developed, you see it on the left-hand side. This helped our students to deepen the understanding of sound as a spatial phenomenon, and also not to be biased by the typically two-dimensional representation of frequencies. We also tested the use of digital acoustic simulations for their use for the benefit for geometry formulation, for evaluation variations, as well as predicting and validating a desired performance. In order to assess the initial situation, a standardized acoustic measurement was carried out, which you see on the image. The setup for the digital simulation is analog to the actually conducted acoustic measurement, whereby 6 receiver positions are measured with 2 speaker positions, and the 12 measurements are interpolated respectively. In the end, we found that there are 3 main obstacles for implementing an acoustic an associative geometry model directly influenced by simulation data, i.e. using simulation in order for geometry formulation. First of all, there's the lack of there's a lack of a direct relation between geometry and reverberation time that I mentioned before. Secondly, there is the potential fuzziness of the space and unknown materials which impede the formulation of simulation parameter. And secondly, and most obviously, there is, as I mentioned, a significant performance problem. However, we also did try some after-the-fact simulations with already more elaborated designs to analyze whether it can benefit for comparing variations and predicting the intervention's performance. Here we found that the realized ceiling in the end outperformed the simulated one significantly. This shows that a meaningful prediction can only be made when absorption coefficients for all the materials are known in the specific installation situation. In our case, the absorption coefficient was only given for a standard way to install the sound-absorbing material. And well, we believe that although the simulation may lack precision in order to make reliable quantitative predictions, we still believe that it is valuable for comparing variations, because the potential inaccuracies for absorption coefficients in the simulation, they apply for all the different variations. But now let's have a closer look on the realized acoustic ceiling. The room contains clearly locatable and basically immovable sources of noise. We have the working tables along the window. There is a working table and a small kitchen area. The geometry of the sound-absorbing elements under the ceiling, they are dependent on the proximity to these noise emitters. The closer they are, the smaller the units become, which you can see in this graphic and here as well. and they fold more and more into the space, generating a larger surface for sound absorption, and at the same time constituting angled polygonal surfaces for sound scattering. The structural basis of the acoustic ceiling, it's made from slender frames fabricated from birch plywood, and Lanisor, a sound-absorbing polyethylene felt, is used as an infill within these ones. The aim was that the acoustic ceiling should not only work for the given situation, but it should also be applicable to different rooms and different environments. Consequently, an associative model for adjusting the design and adapting it to specific spatial and specific acoustic situation was developed. At the same time, this model generated all 3D representations and the fabrication data as well. Milling and cutting are the two basic operations for processing Lanisor, the sound-absorbing polyethylene felt, whereby cutting is faster and needs less post-processing and was thus preferable. White-coated and natural birch wood was used for the material for the frames and all the joints. Further on, only 2D and 2.5D operations were used for the fabrication of the project. And also all parts were only treated from a single side, and we only used materials that were available in standard sheets. These restrictions, they aim for different goals. First of all, they're employing the idea of answering complex questions by a simple means which reflects the philosophy of design production. And these limitations, they implicitly suggest the use of well-established form-finding techniques like bending and folding, which we wanted from an educational side. And it had the nice benefit, which you see here on the image, that we were able to ship 120 square meters of acoustic ceiling on just 6 euro pallets. A consistent part logic is paramount for a project with individualized parametric design solution. Especially the importance of tagging cannot be overestimated when you're dealing with a project with more than 3,500 individual and serialized parts. What I realized when I went through the pictures and saw these pictures, that there's also another nice side effect when architects collaborate with product designers, because they put even more effort and love into the details. I remember hours of discussing the right screw head. Consistent part logic influences the design and manufacturing from identification to assembly of individual parts, but also the structure as a whole. And it also helps you to keep track while assembling of what has been done and what is left to be done. Let me round up the description of the fabrication and installation. The frames, they were consisting of either 3 or 4 elements. They were assembled first and then interconnected to manageable segments. The sound-absorbing polyethylene felt was screwed in from the back and fixed in a adequately prepared seam was then fixed. The assembled frames were laid out for a final check before mounting the segments in rows of 2 to 3 in segments of 2 to 3 rows under the previously installed substructure under the ceiling. Yeah, let me conclude. We believe that the project was a great success in multiple ways. I mean, first of all, it's an eye-catching structure, and we believe it's representing design to production's philosophy. But also, hard facts, the acoustic performance was drastically improved. A standardized acoustic measurement after the installation revealed a drastic reduction of the reverberation time for the relevant frequencies, which is now below 0.7 seconds in average. To contextualize this, the general recommendations for good audibility and comfort in equivalent spaces is 0.5 to 0.8 seconds. And we've heard that this also coincides with a subjective impression of the very content users. Also, despite the overall size and amount of non-standard parts, the structure was economically still reasonably. And as a case study for the implementation of acoustic simulations, we learned a lot. It provided valuable insights. Concerning reverberation time, we learned that reliable quantitative results for early design stages could not be obtained with a feasible effort. Also, the duration of the simulation would have been too long to be implemented into an iterative procedure. Thirdly, the lack of clear dependencies between simulated acoustic performance and macro geometry was another obstacle. The digital acoustic simulations proved to be beneficial for comparing variations in a later stage, nevertheless. But the lack of precision for acoustic performance prediction when installing under unestablished, but it lacked precision for accurate performance predictions when installing even established absorbing materials in a novel way. Generally speaking, we learned that simulations with loose dependencies on material properties and stronger dependencies on geometry are more suitable to be embedded into a design procedure for geometry formulation. However, these limitations led us to a new designerly interpretation of sound phenomena and a novel method of how the formulation of geometry can be influenced by acoustic parameters. In the image you see a part of the realized acoustic ceiling which shows both flat and only absorbing elements as well as the three-dimensional absorbing and scattering elements. In this way, the acoustic situation becomes visually perceivable within this space. Well, summing up, I must say that all participants are very proud and happy about the realized result, and I believe that a project like this is only possible with a partner like Design to Production, which expected something extraordinary, but they also committed themselves to the project, and they put a lot of confidence in our students. And obviously, their outstanding effort they put into the project should be emphasized here. Well, thank you for your attention.